All right, here we have the section 7.2, sampling distributions for sample proportions. We will find the mean and standard deviation of a sampling distribution of a sample proportion. Check the 10% condition to make sure we can do that. Determine if the sampling distribution is approximately normal, and if it is appropriate to use normal distributions, we will calculate the probabilities involving a sample proportion. So the sampling distribution of p hat, how good is it, the estimate of p hat for our sample? So to look at that, what we want to do is take sample sizes of multiple different sizes here. If we're looking at Reese's Pieces and we have a sampling proportion of sample size 25 on the left side and sample size 50 on the right side, and consider the approximate sampling distributions generated by a simulation in which the simple random samples are drawn from a population whose proportion is 0.45 or 0.15. What do you notice about the shape, center, and spread of each? Well, it looks like as we go from the sampling size of 25 to the sample size of 50, standard deviation has gotten smaller, and the mean proportion, which we know to be 0.45, the mean proportion is getting closer and closer to 0.45 as the sample size got larger as well. Okay, so sigma, oops, I need a marker here, sigma of p hat gets smaller as the sample size increases. And it looks like the mean of the proportion gets closer and closer to the population proportion, 0.45, because we have an unbiased estimator. Oops, need to go down a little bit. P hat is unbiased. So the larger the sample size gets, the closer the mean gets to 0.45, the true population proportion. This is for the second one where we're getting closer and closer to 0.15, and we see the same thing. The standard deviation decreased, and the population proportion, or the sample proportion for the distribution of samples, gets closer to 0.15 as the sample size increases. So it's the same whether we were looking at the 45% or the 15%. Okay, so what do we notice about the shape, center, and spread of each sampling distribution? Shape. It looked pretty normal, right? It looked pretty bell curved. The sampling distribution. Of p hat is approximately normal. It gets more normal the larger the sample size looks. More normal as n increases. Center. The mean we found on both of those examples we did with Reese's Pieces turned out to be the population proportion mean as well. So the mean mu of p hat is population mean p, which makes p hat an unbiased estimator. Okay, spread. The standard deviation we noticed on both those Reese's Pieces examples, the standard deviation of p hat got smaller as n increases. Okay, so the sample proportion p hat is directly related to the number of successes because p hat is calculated by taking the number of successes in the sample divided by the size of the sample. That makes sense. So we learned these things about the binomial random variable x, mu and sigma for the binomial. So similarly, we can get to mean and standard deviation of the proportion p hat, knowing that p hat is equal to the number of successes over n. So really, if we're taking the 1 over n and multiplying it by np, we're left with just p. And then if we do 1 over n added into what we already had for the binomial, everything simplifies. We get the square root of p times 1 minus p all over n. So another thing just to really continue to emphasize is that as the sample size increases, the spread decreases. I can see that by looking at the formula for sigma of p hat because we're dividing by n. So the larger that gets, we're going to be dividing by a bigger number and creating a smaller standard deviation. So it makes sense with the formula, but we also just need to conceptually understand that as it gets bigger, as the sample size gets bigger, the spread will decrease and everything will become more condensed. Okay, so to summarize the important parts of a sampling distribution of p hat, a sample proportion, the mean is going to be p, which is the population proportion, and the standard deviation will be calculated by taking the square root of p times 1 minus p all over n. And again, that's only if we have the 10% condition satisfied, which is that our sample size is less than a tenth of the population. Mentioned before that as n increases, the sampling distribution becomes more normal. We have to do 2 or more conditions to make sure that we can perform normal calculations with a proportion, and that is n times p is at least 10, and n times 1 minus p is also at least 10. That was something we had to check on the binomial as well. We had to check that np and n times 1 minus p is greater than 10. Okay, now let's use this, check our understanding. 75% of young adult internet users watch online videos. Suppose that a sample survey contacts a simple random sample of 1,000 young adult internet users and calculates a p hat proportion in the sample who watches online videos. What is the mean of the sampling distribution of p hat? If we know the population proportion is 75%, then the sampling distribution proportion is going to be the same. So mu of p hat is the same thing as p, which is 0.75. The reason for that, if we want to explain our answer, is that mu of p hat is unbiased, or p hat, sorry, just p hat is an unbiased estimator. That's our explanation there. Find the standard deviation of the sampling distribution at p hat. Also checking that the 10% condition is met. So sigma of p hat is the square root of p, which is 0.75, times 1 minus p, which is 0.25, all over the sample size, in this case, which is 1,000. Since these can tend to get pretty small, standard deviation of a proportion is always a decimal, so I would say we should go to 4 decimal places, 0.0137. Check that the 10% condition is met, so is 1,000 less than or equal to 1/10 of the population? Yes, definitely. There are many internet users than 10,000. So that's the 10% condition. Now we have this large counts condition, which is the second part of it, where we have to test that NP is at least 10 and N times 1 minus P is at least 10. Well, if since N is so large, really, 1,000, that's definitely bigger than 10. And 1,000 times 0.25 is also definitely bigger than 10. So that's definitely met. If the sample size were 9,000 instead of 1,000, how would this change the sampling distribution? Mu of p hat would not change. We're still going off of the population proportion, 75%. The only thing that changes and that uses the n is the standard deviation. So we're still going to be normal or approximately normal. The mean of p hat is still going to be 0.75. The only thing that changes, like I just said, is sigma of p hat, which now instead of dividing by 1,000 in this equation is going to be dividing by 9,000, which when I calculate that out is 0.0046. Oops, that looks terrible. So it makes the standard deviation smaller and makes the distribution of the sampling distribution rather more normal, more condensed. Okay, this is what the sampling distribution of p hat looks like with many different values of p, where the mean is in the middle, value of p, and the standard deviation, p times 1 minus p all over n square rooted, is the average distance away from the mean, right there. As the sample size increases, our standard deviation is going to decrease and become more and more normal. Okay, one more example. A polling organization asks a simple random sample of 1,500 first-year college students how far away their home is. Supposing that 35% of all first-year students attend college within 50 miles of their home, find the probability that a random sample of 1,500 students will give a result within 2 percentage points of the true value. Show your work. So state, what we need to find, state here is the probability statement that we're trying to calculate, and then we need to know what the uh, sampling distribution mean and sampling distribution standard deviation are to answer this question. So right now, as stated, to be within 2 points of 35%, we need to be between 33 and 37 for our p hat value. And then we need to state, since it's part of our distribution and important, we need to state the mean of our p hat distribution, which is 0.35, which is the population proportion. It's always the same. And the standard deviation of p hat is the square root of p times 1 minus p all over n, which is 1,500, 0.0123. We have to state that our 10% condition is met and large counts are met. 10% condition. Are there more than 10 times the sample size of college students? Yes. And then large counts, and p has to be at least 10, and n times 1 minus p has to be at least 10. That's also met because our sample size is so large that they're definitely going to be larger than 10. So now for our calculations, we're going to turn that probability statement that we stated up above, we're going to rewrite that in terms of z with our additional information for mean and standard deviation. So the 0.33, we have to subtract our population proportion, 0.35, divided by the standard deviation we calculated, 0.0123, which is going to change our p hat statement into a z statement. We have 0.37 minus 0.35 all over 0.0123 again. And our z-scores are negative 1.63 and positive 1.63. When we're between two z-values like this, we have to find the probability of being less than the larger one and subtract the probability of being less than the smaller one. So the probability on the table of being less than 1.63 is 0.9484. And the probability of being less than negative 1.63 is 0.0516. When I subtract those, I get 8968. So what is that even telling us? We just did all these calculations. What are we even answering? That's the last thing. Answer the question. Find the probability that a random sample of 1,500 students give a result within 2 percentage points of the true value of 35% live within 50 miles. So we got about 90% or so, about 90% of all simple random samples of size 1,500 will give us a result between 2 percentage points of the population proportion. Okay? So the next slide just summarizes what we did. And the homework on the bottom.